Right, hi folks, and welcome back to Physics with Captain Rod. I always like starting my videos like that for some reason here. So, what we're going to do today is we're going to chat a little bit about capacitor combinations. So what we're looking at here, we've got this picture of this probably 12-volt battery here hooked to a capacitor of a value, we'll say C1, and another value, or another capacitor of a value, let's call C2. Now, this type of configuration is a special type of configuration. This is called a series configuration. And basically what series means is there's really one loop here in the circuit. This represents a switch in the circuit, and what we're going to talk about during this video is a way to simplify this capacitor system down to a single capacitor system called an equivalent capacitance, and then use that to backtrack and figure out charges and voltages across this pair of capacitors. So, first of all, let's talk about closing the switch here. When we close the switch, what's going to happen is this. We have this positively charged terminal that's going to attract electrons. So electrons are going to want to move in this direction all through this entire system. If we pull electrons from this plate, that's going to leave this positively charged. If the electrons jump onto this plate, that's going to leave that plate negatively charged. And then here we'll have plus, and then here minus. So the capacitors are now charged to a pair of values here. For now, let's just call that Q1 and Q2. Okay. A very important thing to realize about these series circuits is this, that basically for every electron that ends up going to the positive terminal, an electron will leave this plate, one will move over onto this plate, one will leave this plate, one will jump onto this plate, and one will leave the battery, basically. So that's got a very important mathematical consequence for these charges here, and who can tell me what that consequence is? If every time a electron gets added to this plate, one leaves here, one jumps onto here, one leaves here, what's the consequence for these charges?
They don't change. The net charge on them doesn't change.
You're getting there. Nope. Let's say 10 electrons jumps onto this plate, 10 leaves this plate. 10 electrons get added to this plate, 10 leaves this plate. So what can we say now about these charges here and here? Remember that this Q1 is representing the charge imbalance here on this capacitor. The Q2 is the charge imbalance on this capacitor. They are the same. Yep. So in a series combination, assuming these charges started the same, in this case I was assuming 0, then the charges on the capacitors must be the same. So we don't really need a 1 and 2 anymore on this. We'll just get rid of these. All right. So now the idea here is we want to be able to calculate what's called an equivalent capacitance. And the equivalent capacitance is a single capacitor that could be put in the place of these two, where the battery effectively wouldn't know the difference. And we're going to call that C equivalent here. Now, in the circuit diagram here, what we do is we put a voltage symbol for the battery. And I think this is probably the first time in this class I've discussed this, but this is the symbol for a DC voltage source, this kind of short and long lines here. The long line represents the positive terminal of the battery, the short line, the negative terminal of the battery. Sometimes you'll see these in books with multiple lines like so. I usually just draw 2 just because it's more efficient. And so here's what our circuit then looks like after we close the switch. We've got a positive charge on this side, negative charge here, and then we would say that this capacitor is charged to a value Q here that we'll talk about in a moment. Now, one of the things that I think really help when you're dealing with circuit problems, I like to color code the potentials. I think that goes a long ways towards understanding circuits and voltage and how they work here. So when we look at the battery, the positive terminal of the battery is at the highest potential. Now, the reason, if this is positively charged, negatively charged, the electric fields between them would point to the left. And remember the magical sentence here, electric potential always drops in the direction of the field. So this is the high potential side of the battery. in this picture, this would all be at one potential. Okay, remember I call it my IFACS video. One of the very important IFACS was, what's the relevant one here?
The charges on this outside.
That's one of them, but not the one I'm fishing for.
E charges is 0 and potential is constant.
That's it, right there. That the conductor itself is an equipotential. So this is all conducting material because this is made with wire. So this is all constant potential up to this point. How about the electric field direction? Imagine this between these plates right there. Who can tell me the electric field direction due to this plus minus? It will be to the left. So which of these plates is at the higher potential, the right or the left? The right. All right, so there's a potential drop now across this capacitor. So I'm going to color code this a different color now. Now this is all one potential, all constant, right, because this is conducting material. But this plate is now at a higher potential than this one. And again, imagine electric fields here would point to the left. So there are 3 potential differences in this problem. Color-coded, they are red to black, red to orange, orange to black. Now, in this picture, if I color code this potential here, this is this plate right here. And this is all one potential because that's all conducting material. And then the other side here is, I'll just leave it black, that would represent this side of the circuit. All right, some actual math that we can apply to this now. When you're dealing with capacitance, remember that capacitance is charge over voltage. So when you were dealing with capacitors, these are the things you were talking about. And let's talk about the voltage now. You notice that we have red to black, that's the voltage of the battery. Black to orange, orange to red. So if I've got these voltages here, let's say the voltage of the battery, the voltage off capacitor 1, across capacitor 1, and the voltage across capacitor 2. What's the relationship between these two? Not quite equal, but you're probably on track. The voltage across the battery is some combination of these two. What would it be?
Is it additive?
It's additive, right? Black to yellow plus yellow to black, it gives me black to red in the picture. So that means the voltage across the battery is equal to the voltage across capacitor 1 and the voltage across capacitor 2. Now,
Would that mean that the more capacitors there are, the higher voltage battery would be, or is that?
no, the voltage of the battery is a fixed quantity for any given battery here.
So that means that less voltage at each capacitor, depending if the voltage of the battery is say like 9 volts, and you have 3 capacitors versus 2, then the voltage at each capacitor would be less.
Correct. Yes. If you have more if you add more capacitors, the voltage across each one would drop. Yep. That's exactly what we're going to be taking a look at here when we start looking at some of these problems. So, just from the definition of capacitance, it's pretty easy to see that voltage can be written charge over capacitance. So this voltage can be written, looking at this picture, this charge over this capacitance, C equivalent here, because the voltage across the battery is the voltage across our equivalent capacitance. And similarly here we got that voltage 1 can be written Q over C1 and voltage 2 can be written Q over C2. And let's go back now, what did we decide about these charges? They were the same. So they can be divided out of this. So we get this relationship here. We got 1 over C equivalent is equal to 1 over C1 plus 1 over C2. This is how equivalent capacitances are calculated for a series combination. I started this assuming 2 capacitors, but had there been a third one in series, we would have a 1 over C3 and so forth. I think what I want to do here is, so that these don't get too long, I'm going to separate this off into another video here. So, whoops, let's get that back. So that's how capacitors, stop that. This is how capacitors are calculated in a series combination. Some numerical examples will follow.